Welcome to this lecture number 40, the final lecture in this course on NPTEL course on fluid mechanics for undergraduate chemical engineering students. So, in the last lecture, it is good to recapitulate what we have done and so far in this course in a very condensed manner, and we would also like to see what are the things that we could not do in detail because of lack of time or because of the fact that this being the first introductory course in fluid mechanics. So, this is the plan for this course. This lecture, that is, we will first summarize the key concepts that we discussed in this entire course, and then we will finally also discuss topics that we could not finally mention topics that we could not discuss in detail, but nonetheless which are very important in chemical engineering fluid mechanics. Okay. So, in the very beginning of the course, we started with hydrostatics. Hydrostatics concerns with motion of fluid only under static conditions, that is no flow. Okay. When there is no flow, if you take any fluid element, volume element, okay, at each and every point in the fluid, there cannot be any shear stresses. So, the force has to be directed. Suppose you consider unit normal at each and every point on this arbitrary volume element, the force has to be completely in the direction of the normal. Okay. It turns out that that force is compressive, so it is acting in the direction of minus n, okay. But this, if you call n as the unit normal at each and every point, okay, the force should be along the normal. Okay. There cannot be any shear stresses under no flow conditions, because a fluid cannot support non-zero shear stresses under static conditions. The moment you have non-zero shear stress in a fluid, it will start flowing. So, by restricting to no flow conditions, we can make an important conclusion that the forces acting on any arbitrary fluid element, they are purely normal. That normal force is usually compressive in nature, that is, it acts in the direction of minus n, and the magnitude of the normal force is actually the pressure. Okay, that is the pressure in the fluid. Okay. So, once we understood that the fact that there is suppose you consider any arbitrary fluid element, the fluid surrounding this arbitrary fluid element exerts a surface force on the surface, and that acts in the direction of minus n, that it acts inward and it tends to compress the fluid element. Okay. Now, then by doing a force balance on, suppose you have a fluid element under the influence of gravity, okay, we took a volume element and we then said that the pressure in a fluid now has to, suppose you consider this to be Z, suppose this is atmospheric pressure, okay, and if you consider the distance from the free surface downwards as Z, and let us say gravity is acting like this, then we said that the pressure in the fluid at each and every point is no longer a constant in the Z direction, because the pressure has to increase so as to balance the body force that acts on a given parcel of fluid. Suppose you consider a volume element like this, okay, there is a net force acting downwards, which is the mass of this element times the gravity. So, the pressure has to be larger here to support this force in order for the fluid to be under static conditions. That gives rise to this famous pressure variation under static conditions. P is P atmosphere plus rho g times Z, where Z is the distance from the free surface into the fluid. Okay. Now, once we know that part, suppose you have a free surface, this is atmospheric pressure. Okay. Now, if you have any object, okay, could be a solid object, and then if you want to know what are the forces acting on the solid object, then all you have to do under static conditions is to integrate. So, if this is the normal, the pressure acts in the direction of minus n. So, the pressure is force per unit area. Okay. So, this is P times minus n, the vector that is acting in this direction. So, you simply have to integrate P times minus n over the surface of the object, okay, area of the object, okay, area of the body, surface area of the body. Then you will get the net force due to pressure that acts on submerged objects or partially submerged objects and so on. And this gave rise to the Archimedes principle, that once every body, if you consider any body that is present, okay, if this is atmospheric pressure, if you consider a body that is immersed in a fluid, okay, then there is a net force that acts in the upward direction, that is called the buoyancy force. That is because of the fact that the pressure varies with respect to the Z direction, and that means that the pressure, the net force, suppose you consider a simple geometric object, you consider a cylinder, okay, that is immersed in a liquid solid cylinder, let us say, the net pressure force here will be larger than the net pressure force here, and the difference will lead to a net force upwards, that is called the buoyancy force, and this is the Archimedes principle. Okay. And these are the topics that we dealt with in hydrostatics or fluid statics. Then we went to kinematics. We told that kinematics is that subject that deals with description of motion without reference to the forces that cause the motion. So, the description of motion, okay, without reference to any forces that cause the motion, the description of motion as such. Okay. And in that context, okay, we had come up with an important concept of substantial derivative. The substantial derivative plays an important role, because often in a fluid, if you want to know what is the rate of change of a quantity as you follow a fluid particle, okay, we will choose the so called Eulerian coordinate system in fluid mechanics, wherein you place a coordinate system with respect to a lab frame of reference. So, if you take the partial derivative of any quantity like temperature with respect to position, okay, this means that you are measuring the temperature at a given point in space, partial derivative of temperature with respect to time at a given point in space. This means that you are keeping the spatial coordinates or the location of the probe constant. But often we want to address the question as to what is the rate of change of temperature or any other quantity as you follow the motion of a fluid particle. Now, that is given by the substantial derivative. So, this is the time rate of change of any quantity, okay, following the fluid, as you follow the fluid particle. So, essentially this is denoted by this capital D symbol. The substantial derivative of, let us say, temperature is not just equal to the local derivative, okay, but there is also an convected acceleration or convected increase of temperature because of the fact that the fluid is moving, okay. And if there are gradients in temperature, spatial gradients in temperature, then if you move from a region of lower temperature to higher temperature, okay, as you follow the fluid particle, of course, its temperature is going to change. So, therefore, this is called the local time derivative, the partial derivative. This is called the convected increase in temperature, convected change in temperature, and the addition of these two will give rise to the substantial derivative of any quantity. So, in fluid mechanics, we are interested in, for example, acceleration. Acceleration is not equal to simply the rate of change of velocity at a given location in space, okay, but acceleration refers to the rate of change of velocity as a fluid particle is followed. So, it is naturally given by the substantial derivative of velocity, okay, and that is simply equal to partial v partial t plus v dot del v. Okay. Now, we then discussed the notion of, okay, streamlines. A streamline is a line where in which the velocity vector is parallel at each and every point along the line. So, we consider each and every point, okay, the velocity vector will be parallel to that point. Okay. So, by definition, there is no normal flow normal to the direction of streamline, because the velocity is parallel to at each and every point along the streamline. Okay. So, this means, okay, that if you consider a tiny displacement dx along the streamline vector, okay, and you consider the velocity vector, since they are parallel, the cross product is 0. That gives rise to the equation of governing a streamline, which is dx by u is dy by v is dz by w, where v vector, the velocity vector, is given by u times I plus v times j plus w times k, namely the 3 components along the 3 Cartesian directions x, y and z directions. So, these are the u, v and w are the 3 scalar components of the velocity. Now, just as substantial derivative told us how to convert time rate of change, how to get the time rate of change of any quantity as you follow the particle, the Reynolds transport theorem pertains to a macroscopic body Okay. Often we make the distinction between system and control volume in fluid mechanics. A system, for example, contains the same set of mass points. Suppose you mark each and every point in the fluid with some dye, it is a thought experiment. Then as the fluid flows, if the system will contain the same set of points as the fluid is flowing, whereas a control volume is a fixed region in space. It could involve, for example, a device like a pump or a pipeline and so on in space that could contain various unit operations or equipments, whereas a system is actually, it has the same set of mass points. Material points. Okay. So, often many fundamental laws such as Newton's second law of motion is applicable only to a system, because a system is an identifiable piece of matter, whereas a control volume is merely a fixed region in space. So, therefore, when we want to apply balance laws such as Newton's second law or first law of thermodynamics, they are applicable only to a system, but not to a control volume. But using the control volume approach is very advantageous in engineering applications, because you are really interested in what are the forces acting in a given region in space, rather than the forces acted upon or forces exerted by the fluid as you follow the fluid element, because ultimately you are essentially interested in some devices and some fixed regions in space, such as a pipeline network and so on. So, the control volume approach is very advantageous in practice. Okay. This is what is followed, but the fundamental laws are applicable only to the system approach. So, we need a vehicle, or we need a way to sort of transfer the results from the system approach to the control volume approach, that is given by the Reynolds transport theorem. Okay. So, what this means is, suppose you have a quantity such as mass, momentum or energy, which is denoted by this symbol n. So, the rate of change of that quantity of in a system at time t. Okay. So, the way we do it is, we construct first a CV of interest, and then we say that the system and CV coincides at time t equal to 0. The yellow line is the system. At a later time, the system would have moved elsewhere, but while the CV will remain at the same point, at the same place. So, the rate of change, the infinitesimal rate of change of a quantity such as mass, momentum, energy present in the system. So, this, for example, is an exaggerated version. After time delta t, system would have moved elsewhere, is equal to the local rate of change present in the control volume. So, eta rho dV, where eta is n divided by mass, the specific quantity. For example, eta is 1 if n is mass itself, eta is just velocity if n is momentum, and eta is half v squared, for example, if n is kinetic energy, and so on. Plus, this is not all, this is the local rate of change present in the control volume, plus the surface flux term. That is because as the system moves out of the control volume, it also takes material out of it, and that surface flux will also take away whatever mass, momentum or energy. So, the Reynolds transport theorem is in some sense the analog of the substantial derivative. The substantial derivative refers to pointwise change as you follow a given mass point. Here it is almost like a collection of mass points, a macroscopic collection of mass points, which is what we call a system. And as you follow the system, then how does the rate of change of any quantity, how does mass change as the system moves from a given location to another location, then how does that relate to quantities or variables pertaining to the CV. That has two contributions, the local rate of change of that quantity in the CV, plus the surface flux contribution, that is because fluid comes in and out of the control volume by virtue of through the control surface. The physical interpretation for this term is like this: V dot n dA is the volumetric flow rate through an infinitesimal patch, and rho is mass per unit volume. So, if you multiply this will give you the mass flow rate. If you multiply this, which is quantity per unit mass, so eta times mass flow rate will give you let us say the quantity per unit time, okay, due to surface flux. Okay. So, this is the Reynolds transport theorem. Okay. Now, we want to derive the integral balances of mass, momentum and energy using the Reynolds transport theorem. It is very easy, because for mass we have to simply set eta is 1, okay, and dn dt dm dt, if n is mass, okay, if you follow the same set of mass points, that is, then the rate of change of mass of the system is 0. This is the principle of conservation of mass, or the law of conservation of mass. So, this is equal to the local rate of change rho dV, okay, plus the convected or the surface flux contribution, which is rho v dot n dA. Okay. So, this is straightforward application of Reynolds transport theorem. This implies that d dt of integral rho dV over the control volume is equal to minus integral rho v dot n dA. Now, let us try to understand this minus sign. Suppose you have a simple case like this, fluid is coming in and going out, okay, and let us say the yellow is our control volume. Okay. Now, the key thing that we emphasized many a times in this course is that n is a unit outward normal to the control surface. So, at inlets the velocity and the control and the normal are in the opposite directions is negative, v dot n is negative therefore, and at the outlet v dot n is positive. So, if this tells you the net, this term tells you the net mass flow in or out due to the surface due to the flow in and out of the surface. If rho v dot n is positive, that means that there is a net efflux of fluid, and notice that there is a minus sign here. So, that means that the time rate of change of mass present in the control volume will decrease with time. So, that makes physical sense. If there is a net efflux of mass, of course, mass present in the control volume will decrease with time. But if v dot n is negative, there is a net input of mass, then negative of negative is positive. That means the time rate of change of mass present in the control volume will increase with time. So, that is the interpretation of the integral balance of conservation of mass. And for an incompressible fluid, rho is constant. Okay. And so, the mass conservation equation simply becomes v dot n dA is 0. Okay. And so, that is the simplest form of mass conservation equation. If you assume uniform velocity at the various inlets and outlets, then you will get summation v dot n times I, where I is the ith inlet or outlet, and notice that v dot n is negative for inlets and v dot n is positive for outlets. Okay. And this is the simplest form of conservation of mass. When the flow is incompressible, then the density is independent of time. So, then that clearly means that the only way in which there is no way in which the mass v dot n can be different at inlets and outlets. Okay. The other special cases, of course, you can say that the flow is steady. When the flow is steady, then d dt of this is 0. Okay. And then you will get this is equal to 0, but rho is not a constant there, but for an incompressible fluid rho is a constant. Okay. Then we went to the momentum balance, integral balance of momentum, which is essentially a restatement of Newton's second law to a macroscopic chunk of mass points, and then upon applying the Reynolds transport theorem, the sum of all forces acting on the control volume. We said that there are two types of forces that act only along the surface, the so called the surface forces, and then the force that acts on the entire volume of the body, that is called the body force. Okay. And that example of body force is gravity. So, this is equal to d dt Cv rho v dV. This is the time rate of change of momentum present in the control volume plus the momentum influx and efflux due to flow rho v through the control surface. Okay. This is the momentum balance. Okay. And for uniform flow, okay, the key thing in momentum balance is this evaluation of this term, the flux term. So, for uniform flow you can imagine that all these terms are constants. So, you can pull this out of the integral, and integral of dA is simply A. So, this becomes simply, this term simplifies to summation of rho v dot n times A at various inlets and outlets of the system, and of course, we understand that v dot n is positive for an outlet and negative for an inlet. Suppose if the flow is not uniform, okay, then we came up with this momentum correction factor beta, okay, which will enable us to write this equation in this form, but with a beta term in it, and beta is identically equal to 1 for uniform flow, but for other flows such as laminar flow in a pipe, okay, or turbulent flow in a pipe, beta is not exactly equal to 1. So, we can actually momentum correction factor. So, we can take into account the effect of non uniformity in the velocity profile in a simple way by using this correction factors, and we have derived what these values are for laminar flow of a fluid in a pipe and so on. Then we discussed the integral balance of energy. Okay. Now, again it is a restatement of first law of thermodynamics to a flowing fluid, okay, and when you have a single inlet and single outlet, we will see, then the energy balance simplifies to summation over all outlets, summation over outlet. Let's keep it to single inlet, single outlet for simplicity, alpha v squared by 2. Alpha is the kinetic energy correction factor that tells you that corrects for the deviation of the velocity profile from uniform velocity. Out is equal to in minus the amount of shaft work done by the fluid, okay, on the surroundings. So, we took the convention that work done by the CV on the surroundings is positive, work done by the surroundings on the C is negative. So, this if Ws is positive, that means work has been extracted out of the CV. If Ws is negative, then work is being put into the CV, minus the viscous losses. The viscous losses are always positive, okay. WL is always greater than 0. That tells you that whenever you have a fluid flow, there is a unidirectional conversion of macroscopic energy to molecular degrees of freedom, essentially heat. So, that is the loss term, okay, and alpha is the kinetic energy correction factor, okay, that corrects for the non uniformity of the velocity profile. Okay. Now, we also said that this equation has some connection to the classical Bernoulli equation, but one has to be careful because there are the similarities are at times superficial, because the Bernoulli equation, okay, is applicable when there is no shaft work, no losses, that is the fluid has 0 viscosity. It works only for an inviscid fluid or a hypothetical fluid with 0 viscosity, and we try to apply that energy balance to a stream tube and then shrink it to a streamline. So, the Bernoulli equation is valid to essentially to a streamline wherein and for an inviscid fluid. Okay. So, in that case, so when you have a streamline, essentially alpha is approximately 1. So, we said that v squared by 2 plus g z plus p by rho at the outlet must be identically equal to v squared by 2 plus g z plus p by rho at the inlet. Okay. So, there is a superficial similarity between the energy equation and the Bernoulli equation, but one has to be very careful because the energy equation can be applied to across different equipments. You can construct the CV as big as possible, including all sorts of equipments and valves and compressors and so on, pipings and so on, whereas the Bernoulli equation is a special equation that is valid only for an inviscid flow along a streamline. Okay. Then we came to differential balances or microscopic balances of mass and momentum. We did not do energy, but one could do energy as well, and that will form part of the course of heat transfer, because heat transfer is essentially understanding the transport of energy due to flow as well as other modes of heat transfer such as conduction and radiation. So, we did not do the energy balance in the differential sense, okay. That typically forms part of courses in heat transfer. Okay. So, the mass conservation equation becomes d rho dt, okay, plus del dot rho v is 0, or you can write d rho dt plus v dot del rho plus rho del dot v is 0, okay. And this is nothing but the substantial derivative of density plus rho del dot v is 0. For an incompressible fluid, the substantial derivative of density is 0, because if you follow a fluid particle, its density will not change. So, for an incompressible fluid, this term is 0, leaving us with simply this as the continuity equation, and since rho is a constant, that cannot be 0. So, the continuity equation or the mass conservation equation boils down to simply saying that the velocity field, the velocity vector, which is a function of all three spatial directions and time, okay, it always satisfies the divergence of the velocity vector is 0, that is, it is divergence free, okay, for an incompressible fluid. Then we went on to derive the Navier-Stokes equation, the momentum equation, okay, rho times substantial derivative of velocity is minus del p plus mu del squared v plus rho g. Okay. This is a very simple statement of force balance. This is the rate of change of momentum per unit volume. This is this mass per unit volume times acceleration. Remember that the acceleration of a material, acceleration of fluid particle is the substantial derivative of velocity, not just the normal derivative of velocity, not the partial derivative of velocity. So, this is the mass times acceleration per unit volume. So, this is equal to sum of all forces. So, this is the pressure forces acting on per unit volume on a fluid. These are the viscous forces acting on per unit volume of the fluid, and these are the body or gravitational forces acting per unit volume of the fluid, and mu is called the viscosity of the fluid. Tells you how difficult it is to make a fluid flow, because as I have told you, the fundamental distinction between a fluid and solid is that as fluid resists the rate of deformation, it simply does not, whereas a solid resists deformation. That is, a solid casts how much you extend it or deform it, whereas a fluid continues to deform. So, we cannot say that the stress is proportional to or related to deformation itself, it has to be related to the rate at which deformation is happening. So, different fluids will deform at different rates, rather than, so the extent of deformation itself is not a good quantity to think about in a fluid. Okay. So, the Navier-Stokes equation are complex because of the fact that the substantial derivative is a nonlinear term in the velocity. So, dv dt is partial v partial t plus v dot del v. So, here the unknown velocity comes as a product, and these are all partial differential equations, because you have to write this vector equation in three component forms in their individual component forms. For example, you have the x, y, z components in Cartesian coordinate system. So, each component is coupled to the other component by virtue of this nonlinear term, the convective term. So, the Navier-Stokes equations are in general very difficult to solve, but we had made several simplifications while solving the Navier-Stokes equations. But before solving the Navier-Stokes equations, we need boundary conditions, which are, okay, that the velocity is 0 at solid surfaces, at stationary solid surfaces, or if the solid is moving, the velocity of a fluid will take the velocity of the solid. That is called the no slip condition, and that is one type of condition. And at a free surface gas liquid interface, okay, the shear stress is 0 is another type of condition, because the gases typically have viscosity which are of the order of 100 times smaller than the liquid viscosity. So, the shear stress is exerted by the gas on the liquid at the interface has to be very small. So, we can neglect it. Okay. So, the other thing that has to be kept in mind while solving the Navier-Stokes equations is that only in Cartesian coordinate this various terms will become very simple. Okay. That you have these various operators involving del and so on, del squared, I have told you many times that the form of these operators, the gradient, divergence or Laplacian, they are very different in different coordinate systems. So, when you want to solve problems, it is better to take a look at the various forms of the detailed form of Navier-Stokes equations in various coordinate systems that are available in various handbooks and textbooks, instead of blindly generalizing the Cartesian form of Navier-Stokes equations to other coordinate systems. Okay. So, then we proceeded to solve some canonical problems in simple laminar flows of Newtonian fluids, wherein we solved the plane cuvette flow problem driven by the relative motion between two solid surfaces, the plane Poisson flow problem, that is flow in a rectangular channel driven by pressure difference. Then we discussed the pipe Poisson flow problem, that is flow in a pipe, laminar flow in a pipe, and all these enabled us to derive the pressure drop versus the relationship between, analytically the relationship between the pressure drop required to make the fluid flow at a given volumetric flow rate. Okay. So, that was solved, and then we also did one special problem on coating of a wire, and then we asked the question as to what is the diameter of the coated wire in terms of various parameters such as the die diameter, wire diameter and so on. So, we solved all these problems under using various types of simplifying approximations such as steady flow, fully developed flow, flow only in one direction and so on. And we also pointed out that these assumptions are highly restrictive in the sense that even though you find an exact solution to the Navier-Stokes equation, it is not guaranteed that these solutions will be observed in reality in experiments, because the Navier-Stokes equations are a nonlinear set of differential equations, and whenever you have a nonlinear set of differential equations, okay, there could be multiple solutions, and the solution you derive is not necessarily the unique solution. So, it turns out that for example, flow in a pipe, the laminar flow velocity profile or the result for flow rate versus pressure drop obtained using the laminar flow assumption works for Reynolds number less than 2000, but when Reynolds number is greater than 2000, then the flow becomes unsteady, 3-dimensional and turbulent. Okay. So, one has to be very careful while using the simplified solutions of Navier-Stokes equations for newer settings, because it is not necessary for these to be actual solutions to Navier-Stokes equations, but they must also be observed in reality. So, that matter can be settled only by doing experiments to check whether the theoretical predictions are valid. Okay. So, the three major approaches to solve fluid flow problems in engineering, chemical engineering especially, is the macroscopic approach using the integral balances, the microscopic approach using the differential balances, and when both these approaches are not possible, then one has to do experimentation, because especially in chemical engineering, the unit operations involving fluid flow and flow equipment are extremely complex, and that does not allow us to use the fundamental principles of fluid mechanics in using the Navier-Stokes equations to solve problems okay, exactly. So, one has to use the integral balances and couple it with experimental data to find the losses and so on. Okay. In that context, we introduce the notion of dimensional analysis. Dimensional analysis is extremely useful in analyzing experimental data, in presenting experimental data, and in deciding how many experiments to do and so on. Essentially, we did the pi theorem, which says that the Buckingham's pi theorem, which says that if there are n variables and m fundamental dimensions, then n dimensional physical variables and m fundamental dimensions, okay, then there are n minus m non-dimensional groups. There are only n minus n non-dimensional groups. Suppose you have 5 variables and 3 fundamental dimensions, mass, length and time, then essentially you have only 2 non-dimensional groups, and this was the example we gave for the drag coefficient. When you consider drag force as a function of parameters such as the diameter of the sphere, velocity of the sphere, density, viscosity, and finally when you have 5 variables, then when you reduce it using dimensional analysis, it becomes a relationship between the drag coefficient and the Reynolds number. So, it leads to a lot of simplification, because you are now able to present a multidimensional function relationship in terms of just a 2-dimensional function, that is a 1 variable function. So, that is a very important simplification. Quite apart from that, by expressing the experimental results in terms of non-dimensional groups, one is able to now scale up or scale down data, experimental data, to different conditions, provided the actual condition and the model laboratory condition are geometrically similar. So, once you have similarity in geometric scales, and then we can ensure that results such as the drag coefficient, they will be the same provided the Reynolds number is the same. So, keeping the Reynolds number being the same is actually called dynamical similarity. So, keeping the geometrical scales to be the ratios of the geometrical scales to be the same is called geometric similarity. So, once you ensure geometric and dynamic similarity, then the results when presented in terms of non-dimensional groups will be the same for the model as well as the prototype condition. So, this is a very extremely important result, because this is the this is often used in many engineering applications to scale up or scale down experimental data from lab to bigger or smaller scales respectively. Okay. So, once we discussed dimensional analysis, then we moved on. We also while discussing dimensional analysis, we also non-dimensionalized the Navier-Stokes equation, and then we saw that parameters such as Reynolds number popped out naturally by non-dimensionalizing the Navier-Stokes equation, and this also tells us the physical meaning of various non-dimensional groups, and we found that the Reynolds number is essentially a ratio of inertial forces present in the fluid to viscous forces present in the fluid, and we had other numbers such as Froude number and so on. Then we moved to pipe flows. Okay. So, we discussed that when we did simple laminar solution of flow in a pipe, the relationship between pressure drop and flow rate that we got, okay, was not valid for all Reynolds numbers. It is valid only when Reynolds number is less than 2000, when the flow is laminar. After that, the flow undergoes a transition from laminar to turbulence, and in that context, if you want to solve problems in engineering fluid mechanics, it is not sufficient to know only the pressure drop flow rate relation in the laminar conditions. So, we have to go to turbulent conditions as well. So, it is useful to do experimental useful to use experimental data, and there we again use dimensional analysis to say that the non-dimensional pressure drop is called the friction factor, okay, which is essentially delta P by half rho v squared L by d, is a function only of Reynolds number and pipe roughness. Epsilon is the roughness, d is the diameter of the pipe, Reynolds number is rho v bar d by mu. Okay. So, this is the this relation, okay, when plotted graphically, is called the friction factor chart. Okay. Also, please remember that there are two types of friction factors used. This is called the Darcy friction factor. The other friction factor is called the fanning friction factor, which will go something like delta P by 2 rho v squared L by d. So, there is a factor of 4 that that differs between this friction factor and the other friction factor. So, different textbooks can use different friction factors, but one has to be aware. When you use the Darcy friction factor, then the laminar flow relation between the pressure drop and flow rate reduces to 64 by Reynolds number, while when you use the fanning friction factor, it becomes 16 by Reynolds number. Both are equivalent, it is only that the definitions of friction factor are different, but this is only under laminar conditions. Suppose you plot the friction factor versus Reynolds number in a log plot. Okay. So, when the flow is laminar, this relation will be a straight line with slope -1, but after some point the flow becomes turbulent. After the Reynolds number of 2000, the flow becomes turbulent, and when the flow is laminar, the result between friction factor and Reynolds number is independent of pipe roughness, but when the flow is turbulent, okay, it does depend on pipe roughness. Okay, that is an important and this graphical information is used in designing many pipeline networks, in asking the question what is the rating on a pump, power rating on a pump, in order for us to make the fluid flow over a particular distance and so on. Okay. And then we discussed major and minor losses in a pipe. So, these are major losses are because of flow in straight sections of the pipe, okay, and minor losses are because of bends or valves or sudden expansions or sudden contractions and so on. Okay. And once we so the major losses can when you apply the integral energy balance to a straight section of the pipe, okay, and use the friction factor relation, then we can relate the friction factor to the head loss, okay, because the friction factor is defined in this manner. Okay, this is the friction factor. Now, the head loss occurs in the integral energy balance in the form of delta p by rho g. Okay. So, we can apply the energy balance between a straight section of the pipe and then relate the head loss to the friction factor, then you will get this. Okay. So, essentially whenever you have head loss, you can write it in terms of friction factor in the governing equation, and given the Reynolds number range, you can find what the friction factor is and you can substitute that to find what is the viscous loss due to flow in a straight section of the pipe. These are called major losses. Minor losses are characterized. So, when you want to write the energy balance, you will write it as total losses HL major, which is given by this, and HL minor, which is correlated like half k v squared L by d. These are the loss coefficients for various losses, minor losses. Okay. These are the loss coefficients. So, these loss coefficients are documented for various losses in textbooks and handbooks. So, one can use this. The major loss is given by this expression. Okay. Now, having done that, we wrote the integral energy balance plus alpha v 1 squared by 2 plus g z 1 is minus p by rho between 2 points in a control volume by 2 plus g z 2 plus delta h pump is h l t. Okay. So, this has both major and minor parts. This is the work, this is the rating on the pump. If there is a pump that has to be used in order to make the fluid flow from point 1 to point 2, it has to work against the gravitational force, it has to work against the kinetic energy, it has to work against the kinetic energy losses, it has to work against the total losses and so on. Okay. So, this can be used to find the power rating on a pump by using this expression. Okay. By calculating the losses, then we can back out what is the power rating on a pump. Okay. So, we discussed that, and then we move to higher Reynolds number flows, wherein we use the Euler equation without the viscosity term in the Navier-Stokes equation. Okay. Now, using the Euler equation, we derived the Bernoulli equation along a streamline. So, the Bernoulli equation is essentially restatement of the Euler equation, but it is valid only along a streamline. P by rho plus half v squared plus g z is constant along a streamline. Okay. So, this is the Bernoulli equation, and we also said that whenever you have fluid flow at higher Reynolds numbers except close to solid surfaces, the flow is irrotational, that is del cross v is 0. There is no vorticity, there is no rotation, then v can be written as gradient of a scalar function called the velocity potential. Okay. So, when you have del dot v is 0 and v is del phi, then you have del dot del phi is 0, which means del squared phi is 0. So, the velocity potential satisfies the Laplace equation. So, it is much simpler to solve, and then we showed that and then the Bernoulli equation serves to compute what the pressure is. And we said that instead of solving for the Laplace equation, we will use the superposition idea, wherein we have some simple flow patterns such as uniform flow, flow due to a source or a sink, flow due to a line vortex, flow due to a dipole and so on, and by superposing various simple flows, we were able to generate more complex flows, and we said that we could simulate or mimic flow past potential flow past a circular cylinder by simply superposing a uniform flow with a dipole, okay, at the origin. Okay. And by computing the velocity profile, we try to calculate the force due to the pressure forces on the cylinder due to pressure forces. There are no viscous forces in an inviscid fluid. By doing that, we found that there is no force in potential flow past a cylinder when the flow is steady. So, this is a very paradoxical result, because in reality, no matter how high the Reynolds number is, there is always a resisting force that is faced by a solid object due to viscous friction, and since we have neglected viscous friction, that force is not there. Okay. And this aspect was corrected by the boundary layer theory, wherein we said that close to the solid surface, when you have flow past high Reynolds number flow past any solid surface, okay, the flow is uniform far away from the solid surface, but very close to the solid surface the no slip condition has to be satisfied, and the region over which the velocity varies rapidly from 0 at the wall to the free stream velocity is called the boundary layer. And since the velocity varies rapidly, that is the gradients of velocity become large as the Reynolds number becomes large. Therefore, no matter how high the Reynolds number is, viscous stresses will become important, because viscous stresses are essentially eta times dV by dy. So, it is not just that the viscosity is small in order to keep the Reynolds number high, but the gradients become large. So, the product of these two becomes finite. Okay. So, that was the basic idea behind boundary layer theory, and then we solve the boundary layer problem for a flow past a flat plate using a simplifying approach, namely the integral momentum approach, because rigorous solution of the boundary layer problem using the Navier-Stokes equation is a very difficult task. One has to use some sophisticated approximations of Navier-Stokes equations to get to the solution. It is not impossible, but it is not within the scope of the present study. Now, after we finish boundary layer theory, then we move to flow of particulates and fluids, and we move to applications in closer to chemical engineering. Flow of particulates, we discuss settling of particles and how that is used in finding out the minimum diameter that can be captured in a settling chamber. Okay. That is one application we did. We also found that we can derive the terminal settling velocity of a sphere, be it in gravitational field or in a centrifugal field. So, that is one thing that we discussed, and then we discussed flow through packed beds, where you have a bed of particles through which fluid is made to flow, and the question we are asking is purely fluid mechanical type question. What is the pressure drop required to make a fluid flow at a given flow rate through a bed of particles? And we found that by modeling this bed of particles as a bunch of tubes present, a bundle of tubes, okay, with the same porosity and the same surface area per unit volume, provided that is the same between the real situation and the simple model, then we were able to derive a simplified relations for pressure drop versus flow rate. And what is interesting is that despite this drastic simplification in the model, we were able to get the functional form up to a dimensional non-dimensional constant, which was fixed by experiment, and this gave rise to the Cosny-Kármán equation. And we also found that when the flow is at low Reynolds numbers, at high Reynolds numbers, we could use the fact that the flow is through very rough tubes, and therefore the friction factor is constant. So, we got the Berg-Plummer equation. By combining these two over all Reynolds number ranges, we got the Ergun equation for flow through packed beds. Then we discussed flow through fluidization, that is, when you have a bed of particles, we keep on increasing the flow rate. Initially the pressure drop will increase, but after a point when the drag force on the particles overcomes the weight of the bed, then the whole bed will be suspended and these particles will start moving, they will not be stationary anymore, and that state is called a fluidized state, which is often used in many chemical engineering reactors, fluidized bed catalyst reactors and so on, fluidized catalytic crackers and so on. And we were able to use the same ideas such as what is the pressure drop for flow in a packed bed, and use that idea to find the incipient velocity required for onset of fluidization, which we were able to do. Okay. Then we briefly discussed simple dimensionless or non-dimensional approach to understanding mixing and agitation, where we came up with the notion of power number as a function of Reynolds number and other geometric parameters. Finally, in the last 2 or 2.5 lectures, we discussed turbulent flows by using what is called by decomposing the velocity field in the fluid to a mean time averaged mean plus fluctuations, and we found that the fluctuations do not go away even if you want to describe only the mean quantities. That is because the fluctuations transport momentum and they come as stresses, okay, and these are called the Reynolds stresses or turbulent stresses, and in order to solve the problem we have to be able to write down an expression for Reynolds stress. In that context, we wrote down this simple eddy viscosity model, where we wrote the turbulent stresses as equal to eddy viscosity times the velocity gradient, and the eddy viscosity was modeled using the Prandtl's mixing length hypothesis in analogy with kinetic theory of gases. And by using simplified forms, physically motivated forms for the mixing length, we were able to get some fairly robust expressions for example, the velocity profile. Very close to the solid surface, you had this viscous sublayer where the velocity is linear in the position from the wall, and a little away somewhere in between from the center and the wall, you had this logarithmic velocity profile. And these are all universal velocity profiles, because they do not depend on the nature of the geometry of the flow. That is, it does not matter whether it is flow through a pipe or flow through a rectangular channel or flow past a flat plate. These are very robust universal features on shear flows past rigid surfaces. Once we were able to get the velocity profile, we were also able to further integrate the velocity profile to find the friction factor, and we did find a very reasonable fit with a very reasonable agreement with experiments. So, this is what we covered in this course, but it also is important to understand things that we could not cover and which are nonetheless very important. One aspect is, of course, a more thorough understanding of turbulent flows is very important. Thorough modeling of turbulent flows, which we didn't do, so which could form of a more advanced course in fluid mechanics. And we didn't do the bound layer analysis in a rigorous manner. We did the simplified integral momentum approach, but it is possible to use what is called asymptotic analysis by exploiting the fact that the Reynolds number is a large parameter when in bound layer flow, and then we can derive the bound layer velocity profile exactly, okay, in the limit of high Reynolds numbers. Okay. By throwing away terms that are systematically small at high Reynolds numbers, it is possible to derive the velocity profile in the bound layer. Okay. Thirdly, the flows that we discussed in this course are Newtonian flows, but many chemical engineering applications involve non-Newtonian flows. The key difference between Newtonian flows and non-Newtonian flows are twofold. One is that we assume that the viscosity is a constant independent of the velocity gradient, but in many non-Newtonian flows, the viscosity is a function of the velocity gradient itself. So, that such a behavior is called shear thinning or shear thickening, depending on whether the viscosity decreases with the velocity gradient or increases with velocity gradient. So, non-Newtonian flows show shear dependence or shear rate dependence of viscosity. And secondly, they also show memory effects, they also show elastic effects. Okay. So, they are not purely Newtonian fluids in the sense that they are not purely viscous liquids, they have both viscosity and elasticity. That is why they are called viscoelastic fluids, and many chemical engineering applications such as involving polymeric liquids such as molten polymers or polymer solutions are in fact non-Newtonian, and it is very important to in many chemical engineering processing to understand fluid mechanics of non-Newtonian fluids. That branch of mechanics that deals with deformation of more complex materials is called rheology. So, there is a lot of focus on understanding the rheological nature of behavior of complex fluids, because it has an important bearing on the processing of such fluids. Okay. And another related topic is multi-phase flow. In many chemical engineering applications, you will not have flow of a single Newtonian fluid, you will have maybe a suspension of solids in liquids or suspension of bubbles of gases in a liquid or suspension of one liquid in another immiscible liquid and so on. Such flows are much more complex than single phase flows. So, these are called two phase or multi-phase flows, you could have three phase flow also. So, the understanding of multi-phase flow is very critical in many chemical engineering applications, okay, such as reactors, bubble column reactors and so on, where you do have flow of bubbles in a liquid. Suppose you want to design these bubble column reactors, you have to understand at some level the complex flow patterns that are present in multi-phase flows and so on. Okay. So, these are very important, and in the context of practical applications in chemical engineering, which we did not have the time nor the scope in this course. So, clearly these are very important topics, and it is useful for the students of chemical engineering to get a brief exposure at least at an undergraduate level to all these different topics. Okay. So, with that we will end this course, and thank you for your kind attention.